All right, so this last few lectures, we were introduced all these double null monstrosity things, and then gave some brief sense of the stuff. Oh, let's close this door. Oh, thanks. Um, and then so I stated this well-posedness of the characteristic initial value problem, right? And now what I want to do is instead of just proving that, directly, I mean, again, there's just technical baggage because of the complexity of the system, which is a little distracting for some of the main ideas. Instead, I want to discuss the analog of that result just for like wave equations and simple nonlinear wave equations, and and then we'll go from there. And then we'll sort of see that why once we understand those proofs, you can see why it's true for the Einstein equations. All right, and we're going to really sort of start kind of slowly. Well, let me remind you the setting. So we're interested in characteristic initial value problems. So these are characteristic IVP. All right, and what's the idea of this? Remember, so whatever you're doing, whether it's the Einstein equations or a wave equation or whatever, you're going to start with you have two null hypersurfaces like this. So let's actually focus. So we're going to first focus on just the linear wave equation. So let's right, just for simplicity. So I'm going to write box psi equals 0. All right, and this box really means the Minkowski box. All right, which of course we can rewrite in the like this. Right, or maybe that's self-explanatory enough like that. Or we can rewrite, and then here are all these stupid factors of 4. I have it written somewhere. Though I have incorrect ones scribbled out. And then, so, anyway, I think this is the right one. -4. Seems right. Yeah. All right. This looks sort of, is that correct? Well, we can, well, anyway, equals some stuff, right? du, dv, blah, blah, blah. Anyway, we'll get to that later. That's not the point. So remember, these are null hypersurfaces, so we're going to work. So a lot of these things I'm saying all work much more generally in that you don't need to work with this particular U and V. I mean, what's important is just the geometric thing, that the hypersurfaces are null in the Lorentzian sense, say on Minkowski space, and that they intersect. So we're going to work, let this be some hypersurface V equals, say, V naught. This one, say, U equals U naught. And then I want, so here there's some sphere U V naught. I want the R, the sphere to be something positive. So I want them to intersect, transversely to sphere. In other words, and again, if you're confused what's the assumption, there is another characteristic initial value problem, which is very natural, like from a physical point of view, which would be so this is like, anyway, like this is like the axis is somewhere here, right? And then you have these cones coming out, the cones coming in, and all these cones, so these cones all intersected spheres, right? And I'm looking at like some piece like this, and I want to go to the future. There's another natural characteristic initial value problem, which you could try to study, which would be to start at a point, right? And just look at the future cone coming from that point, and you could try to put data there and solve. I'm not going to discuss that at all here. This one is a much more singular thing, right? Somehow this thing is right here, the things intersect something codimension 1. It's like the natural thing of 2, right? But here somehow it's a further degeneration, and so it's more complicated. Okay, but I'm not going to discuss that. All right, so we're in this situation. Okay, so I assume that somewhere over here is r equals 0, and so something like this. Okay. Um. Oh, I always do this. This is, of course, this is u equals u naught, right? This is u equals. Um. uh, v equals some, so v naught. Okay, so all right, and what do we want to do? We want to put so what do we want to prove for this? So what we want to do is we want to put data on. So maybe if you want for concreteness, you could take so a standard thing. So just standard thing coordinates would be you can think v equals 0, you know, and u equals -1, right, or something like that. Okay. So then you have v if this is v equals 0. So if it's v equals so here's r equals 0, right? You can think so you have u equals -1 coming from here. And then so here is v equals 0. We can write it up here. All right, we're interested and we want to solve. So where does it make so if we're going to put data on those hypersurfaces and solve for the future, the maximum region where that could possibly make sense is in the domain of dependence of them. So that will be in so we're going to put data. So we'll put data along say v equals v naught and u equals u naught and want solution in the kind of J plus of those regions. J plus of the union of those. Right, which just corresponds to, whatever. Okay. All right. So we're going to start with proving this theorem. Well, I'm not, let me state the theorem exactly. And so that's just schematically. So here's all right. So let's give this region a name. I'm going to call this region G. Right? So here's a theorem. I don't know who this is originally by. I'm going to follow this proof. Follow a trick that's due to Rendell, which we'll see that. Anyway, we'll get to it. So let's suppose, and I'm going to work say in the smooth category for now. All right. So suppose let's give So suppose you have so let's say psi out. That's gonna remember this this language out means the one going to the right usually and this one going to the left. So we have psi out is going to be from some function from yeah. So we have to have let's call this hypersurface v equals v1 and this u equals u. All right, so psi out is going to you could think of it as a function of v and theta a. So going from v naught up to v1, right? Can work with real numbers, complex numbers doesn't really make a difference. And then you could have psi in. Right. So given these things, so let's suppose these are all, smooth functions, then there exists, well, in fact, a unique solution, the unique C infinity solution psi in this region G, well, solution such that box psi equals 0. And so when you restrict psi to u equals u naught, you get you get psi out. Oh, and then of course we need this compatibility condition. And we need that psi out at v naught theta a equals psi in at u naught theta a, right? That's just saying that the data sort of induced data is continuous, right? So then you get this, and all right, that's there. Okay. Any questions?
So we do not require any further derivatives of the psi out and psi is to match on it.
We don't, and also that doesn't make sense. You think about the picture, right? They're tangent to along these are these null hypersurfaces coming in. So I mean, if if you think that this is going to eventually be true, so this psi n, which is along v equals v naught, the only derivatives you can take, I mean, you could sort of say spherical, I mean, angular derivatives, but these agreeing includes the fact that their angular derivatives agree, of course. Yeah, so the only derivative you can take of psi n is u. And this one, the only one you can take is v, so there's no like compatibility condition to add. Um, so it's sort of simple. Yeah.
I, I don't understand the set G. It is far away from R equal to 0. The set G, so it's such a good to rotate. Or
I just mean for just for the picture, it's just the domain of dependence of these hypersurfaces.
I imagine the G is not compact.
No, no, no. It's compact. Right? It's just it's the because my data, I'm only putting data on a compact set. So they're
So it does not say this G class.
oh my God, I wrote the wrong thing. I mean the other whatever what's the term?
D.
D, yeah. I just like made a typo. Yeah.
It is far away from R.
Yeah, I just mean that if you want, just because I'm using this particular, in reality, it's about null hypersurfaces and
I see. I see.
it works. But if you want to draw with this, don't worry. I don't want to worry about my coordinates breaking down. Yeah, yeah,
R equal to 0.
yeah, yeah. And I mean everything's translation invariant, so without loss of generality, you can translate your coordinates so that you're far away from r equals 0. So that's not a problem. Yeah. Okay. Thanks. That was sorry.
Should be intersection.
Um. No, I think I mean the domain of dependence of the union. The intersection is just the sphere. You mean here? Or the intersection would just be the sphere. And so there's no domain of dependence of it. Any other questions or comments? Okay, so all right, and so basically there's this funny trick. So what I'm going to show is that if you want to show that all you need to prove this theorem, it's enough to know from what you remember from sort of a standard undergraduate PDE class, which is the following. So our ingredient will be this. Well, it'll actually be a more sophisticated ingredient, but the sort of pure PDE ingredient will be the following. So we'll use that, of course. So the normal, say like t equals 0, the space like initial value problem. So the theorem, right? If say psi naught and psi 1 are both say in C infinity of R3 cross R3, then there exists a unique psi with box this and psi at t equals 0 and dt psi at t equals 0 equal. Right? That's just the usual problem, right? So what I'm going to show is this funny trick, which allows you to reduce this characteristic one to this one. All right. Does this make sense? This is just the regular that you can put data t equals 0 and solve, right? Okay, so let's do that then. All right, so and there's some pretty important sort of in the course of this, we'll see some important ideas which are very useful later for the Einstein equations. Okay, so all right, so we're going to prove this one. All right, so this one we know, I'm not going to prove that one. We'll do this one to prove. All right, so the first step is something which is very important, which is the observation. Let me write in words and then we'll say what it means. So the claim is that we can sort of compute, well, I'll explain what I mean by compute. We can compute the full jet of any solution psi. So any solution psi that exists to the equation, we can compute the full jet of it along, this data. All right, by solving inductively a set of transport equations. All right. Okay, and what do I, so again, the jet just means all the derivatives, all the information of every derivative. So I can, without needing to sort of abstractly solve any PDE, like just, I can work just along v equals v naught, nu equals u naught, and I can compute the full jet of the solution. Okay, so how does this work? Well, the idea is to consider, so we can write our equation. So okay, we have to do right, let's get our factors right. So remember we have d by dt equals d by du dt, so that minus so this is this, and this will be d by dv minus that, right? And so when we plug these guys in, we get two cross terms, so you get minus 4, right? So I'm gonna write my equation. So box psi, I get my minus 4 there. Then I get plus. So remember, an r is going to be what is it? R is 1/2 of v minus u, right? All right, so you have 2 over r. Um, so you get plus 4 over v minus u, and then you get d by, so dp minus du of psi, and then we get plus 4, right, over v minus u squared times this, right? All right, so our equation is that this equals 0, right? Okay, so now, so let's look along. So it's going to be completely symmetric of the v equals v0 and the u equals v naught. So let's look at, say, let's consider this hypersurface v equals v0. All right, and let's think about what my claim is. So my claim was I can compute the full jet, meaning I can compute all the derivatives of psi just by knowing that it's a solution and knowing this data. Okay. Um, so first of all, the first point is, well, if I don't take a d by dv derivative, then that's trivial, right? So, I mean, so all derivatives of, right, so d by du to some power, and let's say all, and I'll write it, maybe I'll write it like this, d theta a, so so alpha is some suitable multi-index. That's okay. This is okay with multi, you know what I mean? I say suitable multi-index, yeah. So some just to count all the angular derivatives. All right, so any angular derivative, set of angular derivatives and a bunch of du derivatives of psi at v equals v0, well, that's easy because those are that's just going to be, if psi along v equals v0 equals psi in, then that's just equal to psi in. I mean, at the point, right? That's a triviality. Okay, so the point is, where do you get the v derivatives? And does anyone have an idea?
The move everything to the other side, right? As the once and then get integrated with that. Right.
Well, yeah, we want to integrate it, but we don't want to write it as dv of some stuff. We want to write it as, yeah, we want to treat this equation as an ODE for dv because we're trying to find dv. And the point is, so what's the idea? All right, so the idea is the following. So let's determine, well, actually, there's one more preliminary step. First step, next step. So this is first of all there. Next thing we observe, so on S here, on here, full jet is also trivially determined. And trivially here means, again, we don't have to solve anything, it's just from the data. Because here on the sphere, we have access to both directions. So you can do all the angular directions, you can do that direction, you do that direction, you're good, right? Right? Because because SU here, a subset of it's a subset of both of these. So you can take advantage of either direction to compute. Okay. So idea to find dv here along v equals this. Well, we treat this as an ODE in the u direction for d by dv. So we write it as -4. To emphasize that when I'm thinking of it as an ODE, maybe I'll even write, well, it's not really an ODE, it's a transport equation, so maybe I'll keep the d by d. So you have d by d, but it's a transport equation that on each, I mean, if you look sort of on each angular, if you fix any angular point on the sphere, it really is an ODE for that fixed theta. So, all right, so let's really write it like this. So it's a d by du of -4 d psi dv. That's what we want, right? Then there's this other term here for, all right, so at v equals v0, I get, of course, this is v equals v naught minus u. Remember, this hypersurface is such that it stays away from r equals 0, so I don't have to worry about this thing is never going to 0, right? Um, times all right. So these are things we don't know on v equals v0. This is all on v equals v0, and then I just put all the other stuff we know, right? So I can put that over here, du of psi over v naught minus this, say -4, right? That's all known, and I mean, yeah, I'll just say, and this stuff is known. And moreover, we also already know this at uv equals u naught, v naught is known. Right? So in other words, so the thing that we don't know satisfies a linear ordinary differential equation with a right-hand side that we know, and we can integrate it from u equals u naught, and we know the data. So there's a unique solution, right? Makes sense? All right, so this gives unique choice for right. And this sort of seemingly silly observation is really, really fundamental. So this point that, if you know the tangential information, so this is a more general thing underlying this, as you can imagine, that if you know the tangential information of a solution, so tangential meaning just the restriction of the solution of a solution to a wave equation on a null hypersurface. If you want to get information about a transversal derivative, so a derivative that's in the going off it, which will be null, what the wave equation itself will give you an ODE for that transversal derivative, right? So if you know that derivative somewhere, of course, if you don't know it anywhere, that you can't get started somehow. But if you know information anywhere on that hypersurface, you can solve an ODE to sort of propagate information from any point anywhere else, right? That is something which is, and in some aspects, that some version of that is true for any like system of hyperbolic equations and even nonlinear ones. And that kind of using such techniques is really, really fundamental for many things in the analysis of the Einstein equations. All right, but this is sort of the simplest manifestation. All right, now, so this gives us d by dv. Of course, I want to get all the possible derivatives, but hopefully it's clear now that you can iterate this. So we can iterate by just by differentiating the equation and repeating. Okay, so now, well, first of all, you can differentiate. So you can differentiate that ODE with, you know, du of I d theta, this for any derivatives. And they won't exactly commute, of course, but it doesn't really matter because you're always going to get some ODE for the new quantity. And the end result is you will still have an ODE for this thing. Oh, sorry. One of the annoying things in this subject is the need for notation to encapsulate all these ways of taking derivatives of things. Um, all right, so then so here we're gonna have dv of du di theta of alpha. All right, so that's the thing I'm trying to show. I'm still just taking one dv derivative, but just showing how once you realize that, the rest kind of follows. So I can differentiate, and then I claim I will get known stuff. So if you think about it. So first of all those derivatives, if they hit, if derivatives hit the right-hand side, well, this is exactly stuff I already know. And then there's the point, this is where there's an inductive procedure. So for example, d by du can hit this term, right? But then, and that will produce a d by dv term, which is not something that we know from the data. But, if one of the derivatives hits this, then that's one less derivative hitting this. And inductively, we will have already gotten it, right? So for example, just to be clear, if we commute once with d by du, that d by du could hit that, and then there would be a d by dv on the right-hand side. But that's already what we solved for this first step. So let me hope you'll allow me to skip writing that out as an induction. I hope you. Okay, and then all right, so that's for one derivative, and now you just have to see. Okay, so this lets us find lets us find everything like this. All right. But what about higher V derivatives? This, by the way, if any of you have looked into null gluing, things like that, I mean, this reasoning is fundamental to that. Um, any questions here? All right, so higher derivatives. So any thoughts? There's almost not much you can do. Yeah, just differentiate the wave equation with V and repeat. All right, but now again, you just have to convince yourself that the structure that we use is preserved by commutation. But again, it's the same reason that the structure was fine here. That well, let's just commute it and just check. So we could commute. So let's commute with, and once we do it for two V derivatives, it'll be clear how to do the induction in general. So let's commute with. Right, the only subtlety is again because it doesn't commute with d by dv. You have to make sure the commutator is fine, but it's fine for the same reason because it'll involve one less d by dv, right? So you commute with d by dv, and well, I'll just say and again, you're going to get your equation. You can write like this now, like dv squared plus 4 over v naught plus u of dv of this, and then this is going to equal some h, right? And then h, you know, h, and all of these derivatives along h. I should say there's a sense in which something that I said is a bit silly, which is you might say, why did I even do this step where I commuted by dui and d theta I? And well, you'd be right, it's a bit silly. Because when I integrate this ODE, I mean I get the function tangentially. So of course it includes the information. But in terms of when you sort of prove estimates, somehow you still might commute anyway. If it's really just a question of the knowledge of the of the anyway, do you understand what I'm saying? Once you solve this equation, deep psi dv completely on this thing. In particular, d by du of it. You don't have to compute with d by du to solve for it, but anyway, you can. All right. Anyway, so I claim so you get this h. So h in particular. All the derivatives tangential to h. H. I want to say along v equals v naught, and so what you see is that it's the exact same structure. Now you can repeat. Okay, and again, the data because you're always going to integrate this from u equals u naught, which is on that sphere where you know everything. So you repeat. Okay. All right. Questions? Again, it's a bit simple. It's like sort of simple observation, but extremely important. Underlies everything, almost everything. All right. So if you were in say, the real analytic category, you could already try to build up just power series solutions. Of course, then you would need to, so the name of the game would be to prove some estimate. You'd have to prove various estimates. So assume your data is real analytic and prove for this full jet, you'd have to establish the estimates for it that, let you do the power series. That's like a Cauchy-Kovalevsky type result with characteristic data. So no, in the normal application of Cauchy-Kovalevsky would require two pieces of initial data because it's second order. But the point is that the normal version holds for non-characteristic data. This is exactly the case with the data is not sad. It does not. You cannot. These null hypersurfaces are exactly where you can't put data in the normal way, but you still can't. So it turns out that in this case, the resolution is that you put sort of one less piece of data because somehow the missing data is already determined by the equation. Okay, check the time. 3:42. Okay, so that's okay. Then we can repeat this on the other one. So this was all on v equals v naught, but same thing works. Same thing works. Nu equals v naught. Okay, so we have the full jet of the solution. All right. All right. Like I said, if we were in the analytic category, that would be enough. But we don't want to be stuck in the analytic category. And so we want to go further. All right. So now, there's something in which I won't say very much about. This is a bit of a distraction, but it's kind of interesting. You should go if you're curious about it. Go read about it. So now you can ask. Now what I want to do is I want to find. I want to find a smooth function f. Let's say on Minkowski space. All right, such that when I restrict f to these hypersurfaces where I computed everything, such that this has the jet we computed. All right, so this is a question of you have a bunch of functions corresponding to derivatives on some set. So you have some closed set, say, or well, not a close. I mean, yeah. Anyway, something where yeah.
What do you mean by has the jet?
So I mean so I computed what psi, we haven't found psi. All of this is if psi exists, then it's all these derivatives are determined. So now I want to but that just determines them on u equals u naught and v equals v naught. Now I want a function, just any function actually will do, one defined everywhere. But I want, for example, that dv of f at u along u equals u naught is equal to what dv of psi would have to be if it were a solution.
Yes. Okay. I see.
If psi exists, we don't know that psi exists, right? Okay, so I want to do that. So this is this question of whether for example, on some compact set you can determine derivatives at different points for a thing. This is a sort of an old. This is something called the Whitney extension theorem. So I won't get into that. You can do it. All right. It's kind of fun. So this exists by the Whitney extension theorem. This basically gives you conditions that you have to check on when on your set and things where it makes sense. And they're so if you have all these derivatives and if you had a smooth function which had those derivatives by like you can do Taylor expansions at different points of your set and there's some, by using like certain Taylor expansions need to be valid and where some other ones are valid and differentiating the Taylor series, you can get some compatibility conditions that have to be satisfied for the derivatives. I mean, you can't put an arbitrary jet and find a smooth extent. You can find counterexamples, but when the extension theorem tells you some necessary conditions and you can check that they work here. I'm going to skip that. You can look at Rendell's, like I said, this part is from this paper of Rendell. This is I forget. If you just look up characteristic initial value problem. Though the one annoying thing here, that paper immediately does the quasi-linear case. So that's a bit of I did some work here to extract the really simple version. Anyway, but you can look if you want, and it gives references. So, okay. So, all right. So we have this function f. Okay. It's still, I mean, so what, right? Ooh, sorry. All right. So now's this trick that I like a lot. Kind of why I wanted to do it. All right. So remember that we had this set G. So let me remind you. So we have this V equals V naught, and we have this U equals U naught, and these are capped. Well, then let's draw here, and then we stop everything at U equals U1, V equals U1, and then I called this set G, right? So now what I'm going to do, I'm going to define a function rho. Oh, and I'm using this function rho appears in his paper, but I find the way what I'm going to tell you is exactly the argument in his paper, but I find for some reason I find it more natural to just define things slightly differently. But beware, this rho is different. It's very, very close. That's why it'd be confusing. Anyway, so what I want to do, I want to define a rho which is 0 in G. So this is going to be a rho is going to be defined again on all of Minkowski space. All right, so I'm going to define it to be 0 in G. And then I want to define it to be box of that function f I got outside of G. Well, let me say actually, I really only well. Yeah, I guess it's fine. No, that's fine. All right. Okay. So so one thing to note about this, so this function rho, so rho will, so here's claim. Rho will be smooth across U equals U naught and V equals V naught. Right? So why is that? It's basically because how we it's sort of how f is determined. So on U equals U naught and V equals V naught, f and all of its derivatives, right? We determine f and all of its derivatives just by setting it to be equal to what the ODEs sort of forced. But if you think about those ODEs, they just come from solving the wave equation, right? And differentiated versions thereof, right? So the sort of those jets take the right values along U equals U naught and V equals V naught. If it, it's a corollary of that, the box F vanishes on V equals V naught. Because the way we computed the jet of psi forces box of F to vanish on U equals U naught union. Right? Okay. Okay. So what's the next step?
But it's not necessarily something across the other two.
Yeah, that's why I was hesitating for it. It's just that it doesn't matter. Okay, you'll see. Because we're not going to, the point is, well, anyway, let me just finish the argument and you'll see why it doesn't matter. Yes, indeed. There's no reason why, I mean, over here, we sort of don't care in reality. Okay, so now I want to solve the following. Now I want to solve the following. Let's solve box of psi equal to rho. And I want to put, oh, I guess there's a question of what this so this hypersurface will be some t equals t naught, right? Depending on which u's and v's I picked, right? So I can draw some constant t there, right? So I want to put these, and I want this to equal f and dt of f equals this. Okay, now I can do this. This is a regular problem, a regular initial value problem. So I can do that. I can put data here. It's true that this, oh, I guess that I didn't put the inhomogeneity when I stayed at the, I told you that you can solve this, right, from your PDE class, but you also learned how to solve this in your PDE class. Of course, you might complain, like Avia just did, that this is not smooth up here, but that's fine. Just solve it in the, you know, yeah, you can solve it sort of. I mean, we only care about things in reality in the past of this region G. So if you want, you can solve in things which are in the causal, um, the, yeah, what do I want to say? Yeah, I'll just say in the whatever interior of the causal path of G, right? I mean, I'm going to do something in here, so I don't care what happens here, right? Okay, and in that region, this is smooth, right? In the interior, so if I'm staying away from there. Does that make sense? The Zoom people can't see me. I stand there. Hope that's not too disturbing for them. Okay. All right. So we're almost there. Does anyone sort of see the punchline? There's like so little going on, it's hard to see where it's going. This is like a sequence of triviality, sort of. Yeah, so inside of G, psi solves the wave equation, so that's a good sign. We wanted to get a solution to the wave equation inside of G, yeah.
And it has the correct jet as F, which is the.
But why? No, but why does it have the same jet as F? That's the key point.
Well, because it solves it well from the space like from you go up a little bit and then.
Yeah, but it's because it equals F inside. This is the trick, right? So think about it. Also, I'll write it, but I'll say it in words first. So in this region, yeah, so there's like, there's kind of a region 1, region 2 over here. They'll treat it the same. So region 1, well, this is right here. So in 1, what's going on? In 1, I solve box psi equals box F, right? And psi dt psi at t equals 0 equals F dtf at t equals 0. But you know how to solve this, right? Psi equals F, right? You just observe that's psi equals F solves FPD, and this is a linear equation. So this is unique. So that means that we have to have, so here psi equals F. And similarly, and 2 is the same. So here psi equals f. But everything is smooth across u equals u naught, v equals v naught. So if you solve the wave equation, with a smooth data and smooth right-hand side, it'll be smooth. So which board am I on? This board, yes. All right, so this implies that so by and also by smoothness of psi, that the jet of psi along here, this is something much stronger than what I'm going to actually need, is equal to the jet of this here. In particular, in particular, as a much, much smaller consequence of that, this restricted to u equals u naught equals psi out, and this restricted to v equals v naught, v naught equals psi in, right? Because f, that's how we got f, right? Okay, and then finally we observe, well, again, in G, box psi equals 0, right? So that's exactly what we wanted. All right, so it's just sort of this funny, Rendell found this funny little trick. So it's a funny trick that somehow, and of course you can invite you to think about whether this smoothness is kind of clearly overkill, right? You don't really need smoothness to solve all these things. I mean, you see what was important. I mean, you needed something. You need some compatibility here. Well, of course, this is a linear equation. You can solve a linear equation with just about anything on the right-hand side. But anyway, you need something. You clearly need something. I mean, you need, right? Maybe you don't need actually these jets don't have to agree, but you need to conclude this at the end, right? Anyway, you can think about what's really necessary for this. But so what he found is, so it's a sort of interesting trick. And also, well, we'll take our break soon, but and we'll see this trick is extremely robust actually, because it's not special to a linear thing. Well, okay, it has some deficiencies that we'll get to, but it gives you statements for for quasi-linear wave equations. It is a some version of this trick will allow you to reduce some kind of local well-posedness statement for characteristic data to deduce it from a corresponding space-like, the usual well-posedness. Right? So with that is to say, you compute the jets, then use some kind of extension theorem to say that, well, I can actually find something bigger, and then you play this trick where you sort of solve some inhomogeneous thing that's cooked up to force it to take the right values. All right. Anyway, that's kind of nice. All right. So let's take our break here. And then so after the break, what I'm going to do is I'm going to then tell you what what the same theorem does immediately applied to a nonlinear wave equation. I'm still going to keep it relatively simple. I'm going to stick with the semi-linear case. And anyway, then we'll take it from there. All right. So let's reconvene at 4:10. All right. So let's get started then. Okay, so now, okay, of course, we're interested in the Einstein equations eventually, and the linear wave equation is not really the right kind of model. Um, all right, and of course, we know. I mean, I've asserted to you at the way at the beginning, maybe during the winter school, that or maybe no, before the winter school, I think, that the Einstein equations in wave coordinates, in some particular coordinates become a set of quasi-linear wave equations. All right, but let's still, in between linear and quasi-linear, it's maybe reasonable to look at the semi-linear case. So let's consider semi-linear. All right, so semilinear means that the nonlinearity does not affect the principal symbol. So that makes things, especially in a problem like this, where remember that we want to, the characteristic initial value problem, you put data on null hypersurfaces. But what is null? It depends on the sort of the metric governing the equation. So if you have a quasi-linear situation, you have the self-referential aspect that the thing you're trying to solve for itself determines, what is null. And okay, now you can resolve that for a certain class of quasi-linear equations, which include the Einstein equations. But I won't get into that in detail here. Well, I will say maybe, okay, since I brought it up. Well, okay, so first of all, what's the semilinear? So the semilinear case is going to be something like this, and now we're going to allow on the other side something which depends on the value of psi, derivatives of psi, but only first derivatives, and then, whatever, your t, x, y, z. So we want to have some analog of the theorem here. So like I said, so for the quasi-linear, so the quasi-linear would be that you would naturally allow, maybe some second derivatives here. All right, that turns out in that level of, well, I mean, quasi-linear, you can allow some things, some second derivatives. So you could have like 1 plus, psi, box psi, something like this. So it turns out here is that the technique basically works, but what's important is that if there are nonlinearities that arise in the principal symbol, at least to naively use this method, they need to just involve the solution itself. Because this which is what happens in the Einstein equations, actually. So for the Einstein equations, the somehow your principal symbol is like the metric you're solving for, contract it with all the derivatives times, the metric solves something like this, right? But here's the point is that the you know the nonlinearity here just involves a solution. It doesn't involve derivatives of the solution. So if you think about that data, characteristic data just involves posing the solution itself, right? So because it just involves a solution here, like the info about this is included in the data you put on the characteristic when you give characteristic data. So it's like sensible to give data where you know that the hypersurfaces are null. Because you say, I want the metric to be this at u equals u naught. I can do that in such a way that u equals u naught is null. Because you see what I'm saying? But if somehow in here there was like dv of g, you would have this self-consistency problem. Like you wouldn't know it was null until you solve for dv of g, but you don't know what dv of g is, and it doesn't work. But this is the Einstein equations are like this, so it actually is fine. All right, one of those many seemingly nice things about the a priori gross looking Einstein equations. Okay, but anyway, I'm not going to get into that. So let's look in Rendell's paper. Okay, so let's consider this case. So again, so we don't have any issue like that in this case, because in this case, again, the principal symbol is governed by the Minkowski geometry. So, all right, so what's the deal? Well, first point is that the linear theorem cannot, the naive analog of the linear theorem, naive analog of the linear theorem cannot hold. Cannot hold in full generality. All right. And why is that? Well, you can already see that at the level of so what would the naive version be? The naive version would be again that well, I guess they're like they're varying levels of naivete that you might have. I guess the most naive version would be that you get a global solution again. I mean, that one, let me hope none of us would be so naive as to think that, because we know nonlinear things blow up. But so what is the naive generalization? Let me say. So the naive generalization is the theorem basically is the analog of what I wrote is true for the Einstein equations. So whatever, I guess last lecture, right? So the naive generalization would be that you do the same thing. So again, remember we're putting the data here, we're putting the data here, And what you would think, you say, okay, I know nonlinear things can blow up, but I'm always allowed to go just a little bit of distance from my data. So the naive thing would be that, well, I can go in epsilon here and some epsilon distance here, and that should be fine. That would be the naive thing. That this is false in general. So this is not true. So this is false in general. And you can see that it's false already at the level of the jet computation. So you can mimic many of the steps. You could just mimic and see what happens. All right, so we can see that this fails. So we can see this at the level of the jet computation. And so what we know is that when we do the jets, these are in principle, the jet is determined by inductively solving a set of ODEs, right? But now those ODEs are nonlinear, so they can blow up in principle. I mean, it's kind of as simple as that. Let me just, for completeness, let me give you an example of one of the ones that blows up because, well, we want to understand what kind of nonlinearities are bad, you know. If we want to, like I said, there's some, this naive version does hold for the Einstein equation. So we'll need to understand what distinguishes the Einstein equations from the sort of generic nonlinear equations. All right. So, I mean, one source of blowup. So this will be this example will be something which is referred to as a called Riccati blowup. It's basically which is just the following ODE. So if you have, so U of t, right? So if you have some U of t, right, which satisfies right this ODE famously, this nonlinear ODE, which blows up in finite time, right? You have this, for example, this solution, right? If I get the sign right, 1 over, right, 1 over, I think U prime equals, I think that works, yeah. Right, so this blows up. So this, for example, so U at 0 is 1, but blows up at t equals 1, right? Right, so this kind of blow up, which is driven by some quantity, derivative of some quantity equals something quadratic. Sometimes, okay, yeah, things that are emblematic of that are called Riccati blow up. Right? And that's a very common type of blow up that you can see. All right, and so let's look at it. So as an example, oh, and here I'm going to get confused with the sign. All right, I think this is the right sign. All right, so let's look at this equation. So let's look at box psi equals, I think I have the right sign, du du of the squared. Okay. All right, and so remember, so why already before we even write anything down, why are these things related? So we know that this thing effectively is when we look at characteristic data, we think of this, for example, so along well, I guess I put this one here. So now, so if I go along the outgoing piece, I can think of this as a transport equation for d by du. So it's going to be d by dv of d by du equals some crap, right? And the d by du satisfying the ODE, this is that same quantity squared. So that's, of course there's other junk, but sort of these kind of, that's the analog of these terms. So t well, the analog of t here will be the v, this propagation in the v direction. And so this, of course, there's other stuff. Anyway, so okay, and then let's do this. And then we're also free to look in spherical symmetry. One of the great things about finding counterexamples is that you're able to, work with a simple object. And when you are proving that a bad thing doesn't happen, then you have to study all the objects. So it's sort of nicer to prove bad things happen. All right. And uh, yeah, So what is this? So in spherical symmetry, if I put spherically symmetric data, then my solution will be spherically symmetric. So so we already wrote these formulas somewhere. Anyway, so we know that we get minus 4 d v of du, and then we have the plus 4 over this of d this. Great. And then this will equal, that's what the equation looks like. Okay, so now, so to do a counterexample, I need to propose some data, then show that you can't solve it. So you can start with something, simple. So let's suppose that I'm trying to do, so let's also consider, let's make this for simplicity, u equals -1. Let's say v equals 0 up to something. And then let's suppose that I said that u psi along u equals -1. I just do something very simple. I just set that equal to 0. All right. And then I suppose that d and then I'm going to get so then this goes up to some, so let's say this is v equals 0, and let's say this goes up to some v equals v naught. All right. And let's say some u equals v naught, but I won't even go there. I'm going to focus on some region around this guy. All right. And then all right, so I want to solve here. I'm going to put this can be whatever. This can be, anything, except I just want one constraint, anything such that du of psi restricted to so uv equals -1, 0. I'm going to want this to be very, very big. Right? So this is maybe, again, considering this example I gave, and when I'm trying to do a counterexample, it's not too surprising, right? So I want to sort of show that this thing blows up because of some mechanism like this. I want to make it blow up in a certain amount of, before this v equals v naught, basically. I want to show some counterexample to show that I can't get a solution here. So in order to have blow up at a certain time, I need to if I start very, very small, then of course I will exist longer and longer, right? As you could even see here, right? Of course. Like if your solution is if u at 0 is size epsilon, then you in principle have to wait time 1 over epsilon to blow up, right? So, all right, so I want this derivative to be very large. But the point is, I mean, this thing can be very large. It's completely compatible with this thing being 0 here. There's nothing funny about the data. The data is unobjectionable, right? Make sense? Remember, d by du goes this way, right? So I just make the data here 0, and then it just jumps fast. That will make the d by du be big. Yeah. Okay. All right. I guess in a way I could stop here and just say exercise. So, but maybe it's good just to make sure we're on the same page. So this example you can find in, so there's this other, so I mentioned Rendell's paper. So there's this paper of Jonathan Luke, I think from 2012. I don't know if that's archive or publication date or something, on the characteristic IVP. So he proves the statement for the Einstein equations that with the epsilons. But he has some this counterexample is sort of discussed there in some more detail, or maybe a similar level of detail. Okay, so yeah, so now, all right, so because psi is 0, so now let's look. So let's look at again at this u equals -1. And so what's going on there? So now we know that along u equals -1, because psi at u equals -1 is 0, then dv of it is also 0. So I have this following. So I have dv of, and I guess I can divide by the minus 4 everywhere. So dv of this equals, well, then I put on the other side, equals 1 over v plus 1. Oh, and then I guess you get a minus of du of psi equals plus 1/4 du of psi squared. Does that look right? Yeah, I think that's right. And then, all right, then we just need to, then you just want to complete the square root. So then, okay, so we want to write this as, so we'll write this as 1/2 of d by du, minus of minus, I guess just d by du of psi, yeah, minus 1 over v plus 1 squared, right? So if I square that, I get the 1/4, then I would get minus, then I would get this term, and then it would get plus, so then I have to do minus this, right? Okay, and then I can write this as d by dv of, oh, but maybe my constants are going to be off. But it doesn't really matter. Yeah. I guess so then I just write it like this. So the analog, I need to make this times 2. So this minus this equals, I'll pull this out. So then you have 1/4 times 2.5 squared. And then I don't know why I put that's not squared. Then this thing, so the derivative of this is a 2 over v plus 1 squared. So then I subtract that, so I minus 3. All right, and now this you can just, I think, is that algebra correct? I think. Okay, and then this you can just, well, you can just, and you can show that this blows up. All right, you can, it's an exercise. Show this blows up. Show this blows up for suitable, du at v equals sort of v0 being very, very big, right? Okay, so it's just like a inhomogeneous version of that blow up, right? Make sense? Okay, so that tells you that you can't, somehow you can't just put, data willy-nilly and expect to solve in this kind of region. You can try to soup up these examples. You can ask yourself, well, I think it's a good exercise to play around with these things and think about, well, you might think this is sort of a bad example because sort of already at the level of the jet, you had a problem. You could think, well, what if at the level of the jet, I was fine? Anyway, these are things that are good exercises to think about. I mean, if you're actually interested in, say, working with this stuff at some point, those are good kind of things to think about. But anyway, at the level of this naive version, we clearly can't do it because we can't even, this counterexample shows you that, I mean, it's not even the case that in general, like the jet of the solution will even be well defined there. So you certainly can't try to solve in an open set because you can't even, derivatives not even well defined. Okay, but what does Rendel's argument give you? Well, it still gives you something. You just have to sort of be more reasonable in what you ask for. All right, so wait, so I guess I'm there. Yeah. All right, so here's the theorem, the semi-linear version. All right, so here's theorem. So we're going to consider solutions psi to this semi-linear guy. to box psi equals n of psi deep psi, say t x y z, right? And suppose we're given, the same setting, again, yep, psi out. Let me not write all the things, okay? But now what you get, so in general, now what you get is there exists an open neighborhood. Apologize for the lack of a U. Open neighborhood of U naught of the sphere, U naught V naught. All right, so it's the same thing, right? So this is what we want it to do. We want it to do, here is U equals U naught, here is V equals V naught, and we want it to do this thing. But what I'm saying is there's an open neighborhood of the sphere right here. So meaning you can do, all right, so there's an open neighborhood of the sphere, call it U, such that, such that we have a solution in uh in this, all right, we wanted it in this whole domain of dependence, but instead we get it in this intersect U. Okay. And in fact, there's some more things that you can say about it. Yeah. And I'll say, well, yeah, maybe I'll leave it like this for now. Let's just try to understand the statement. Then there are things you can say about what's very important, all these kind of well-posedness results. What's very important is not just truly this abstract statement that there exists an open set doing something. It's always very important is that in principle, you can bound the size of it in terms of the size of data, like in a normal. So for example, the ODE theorem, it's not, it's much more contentful than just a statement that for any data, there exists an interval where there's a solution. It's also when you can bound from below the size of the interval of the solution and quantitatively in terms of the data, right? That's important. That there's a quantitative, thing. Okay, so this is the statement. It's also you can immediately see why it deals with this issue, right? So if there's some issue about things, some Mercati type blow, because the wave equation, insofar as you can think of it as transport equations for the different d by dv and d by du's. And so if you have a nonlinearity, which is quadratic and the wrong sign, you can get a Riccati type blow up. Well, okay, as long as you just stick to kind of you say, all right, I just shrink my thing so that all my ODEs I just solve locally. And we know ODEs locally are fine, right? So no matter, if this data is very, very big, then I just shrink this thing and then it's okay, right? Okay, that's deals with conceptually that issue. And then, well, in fact, you can now basically run the same proof as before. All right, so what do you need? So, all right, so what goes into this? Right. And again, the reference is the same 2 paragraphs in that paper that were the references for the other theorem. So what goes into this? Well, basically, you can do the same strategy. You just have to replace. So before I was using this like a well-posedness result for a linear wave equation, right? From space-like data. So now you need the analog of for the semi-linear problem.
Our conclusion is that we have a solution in the domain of dependence intersection.
Yeah. So this thing I shaded there.
Yeah.
Yeah. Other questions? No questions on the chat. Chat's been very calm today. That's okay. What was I saying? Oh, yeah, what we need for this. Yeah, so what goes into this? So we need, it's going to be basically the same proof strategy. Plus local well-posedness for nonlinear waves. But the point is local well-posedness for nonlinear waves, right? So again, so remember we did jet computation, then we use Whitney extension theorem to get this F that agreed with the jet. We sort of then recasted everything as this weird inhomogeneous problem, and then invoked the space-like one, and everything worked out. So everything basically is the same. You just the extra ingredient you need is something you need that instead of so we had a global existence for linear things, we need to some analog for nonlinear things. And again, because we're sort of became way less ambitious and we're restricting to some small neighborhood of this little point, it's fine if when we draw this thing and we apply our local theory for the nonlinear one, that the fact that we only can go up a little bit is fine because we're already stuck only going a little bit from the jet computation. So, it all works out. All right, so let me well, I guess I stated, I don't know,
LWP.
local well positiveness. So this I mean I stated this at the beginning of the course. I don't do you want me to write that again? It's okay, yeah. Yeah, it's just right. If you have data in some, well, let's say it's the infinity, then you can go solve for a little bit of time and get something. Okay, so okay. However, we want to do so for what kind of nonlinearities can we do better though? All right. And well, it turns out that kind of if there's a very naive guess and which works, which is basically you just need to pick a nonlinearity so that that doesn't happen. Which just means that you don't want to see dv squared or like du squared. Sometimes this is called the said that they have null structure. So you need a nonlinearity with null structure. This is one of these vague terms that people use to mean almost anything. So many I mean many works in nonlinear waves and general nonlinear PD, it's always like here's this estimate, this key point. It was like, oh, you know, you plug in for the generic kind of term and it would diverge logarithmically and it wouldn't work. But the worst term, but this thing has structure and the bad thing doesn't happen and everything closes and we're happy. All right. And then at some point, people just started calling everything like null structure. um, so what, but there's a reason. I'll briefly explain what this is. So, well, there's some long history about this, which I won't fully get into right now. But I'll just say where the null is. So what we need is let's consider just for simplicity quadratic nonlinearities. All right, so in other words, let's just suppose quadratic derivative. Um, you can, for this kind of thing, you can do something much broader, but it's just for this course, it's good to keep, things get very complicated quickly anyway, so it's good to keep the equations as simple as we can while still being emblematic of the features I want to talk about. All right, so, so that means this might, just something of the form, some particular derivative of this times some other maybe some sum of terms like this, right? Okay. And now all I want to do is let's suppose so we can all I want to do is say as long as you don't see it really is as long as you don't see du of psi squared or dv of psi squared, then the naive version of the theorem becomes true. All right. And okay, so let me quickly say, so what does the word null have to do with that? Well, one thing is you can think if you're studying like a geometric wave, some wave equation, which is coming from some underlying Lorentzian geometry. Now, this is getting kind of vague. You might think that there's some kind of, a nonlinear term is coming from some kind of like metric contraction. There's some metric underlying it, and it's, something like this, right? Now, the point is that in a metric contraction, so our dangerous terms are du psi squared and dv psi squared. So these are, in the Minkowski metric, these are null, right? So in this case, because it's semi-linear, you might think it's kind of like this is like a natural kind of nonlinearity that you can get. But it just, because of the way this contraction works, I mean, you can't, if you plug in two null things into the metric, you get 0. So it's sort of like geometrically natural equations. This is, of course, I'm keeping things right. One thing that's where I've simplified is I'm only considering a single scalar equation. Most interesting equations, well, are not necessarily. Other scalar equations can be very interesting, but many equations in physics are reality systems. Like Einstein equates a system. Then you got much more complicated things, but they're still going to be all sort of governed by some metrics and different contractions or whatever. And whenever you see this thing, it can't be the case that there's UU. So you sort of know you shouldn't see du times du. So that's sort of that's like the structure that prohibits null interactions, right? Okay. So what? 42. Okay. So now let me. I don't know if I'll quite have enough time to say it. All right. So we'll prove this or start to prove this in some level of detail on Wednesday. But I want to what I want to convince you right now is that it sort of reduces to something which is, of course, if you're in the subject, you get used to very quickly. But if you're not, it's kind of weird, which is that the to prove this, um, everything boils down to actually sort of assuming you have a solution to begin with, and then proving that some estimate holds for it, which sounds very weird because you're trying to prove the thing exists. And moreover, you can assume a weaker version of the estimate you're trying to prove while you're proving the estimate. This sounds ridiculous, but it's actually not, well, because I said it in a ridiculous way, it sounds ridiculous. It's actually not so weird. All right, so let's first, so let me try to sketch what's going on though. All right, so first of all, I'm going to just focus on some concrete equation just to make everything sort of simple. All right. And while we're proving this theorem, it'll also be an excuse to see some techniques which are emblematic of the kind of things you do when you study the null. I'm going to do the estimates in such a way that they correspond to things that you would do for the Einstein equations in the double null cage. All right. So let's just as this one simple equation that you could look at. So you can look at so box psi, it's Minkowski box always, and you could consider something like this: du of psi times du of psi. So that's something that well, doesn't have a du squared or dv squared, right? And so in this equation, then it is true that given, again, psi out and psi in, so this one is again defined along u equals u naught, and this one is defined on some finite thing like this. So here's our u equals u naught, here's our v equals v naught, and then we stop everything at some v equals v1 and some u equals u1, that you do get well, sorry, you don't get a solution there. You get some epsilon here. So there exists some epsilon greater than 0. I don't know what to call this region. Maybe call that G epsilon, the shaded region. Right? There exists an epsilon greater than 0 depending on, I'll say Sobolev norms, on a suitable Sobolev norm. So suitable Sobolev norm of these datas, such that a solution, yeah, okay, so there exists this such that a solution, well, unique solution exists in GMs. Okay. So they say Sobolev norm, does that have meaning to everyone? Yeah. Cool. No one's complaining on the chat, so I'll assume total knowledge of that too. Okay. All right. So all right, that's what we want to prove. Okay, so yeah, and so what do I claim that this is going to reduce to? So what I claim is that to prove this theorem, it suffices, ooh, the heck. So it suffices to do the following. All right, so the key step. So I don't know, the key thing to prove for this. And this is what, so if you're in this field and working in it for a while, if somebody was presenting a theorem like this, they would just immediately only discuss what I'm about to tell you, and not even because it would be considered standard why this suffice. So the key thing to prove is the following. Well, you can even rephrase it like this. Assume there exists a solution in G alpha. All right, then there'll be some norm. All right, so we'll define a suitable norm. A norm of the solution of psi. Let's call that psi sub, I don't know, W for wave. All right, there's going to be some norm W. We'll talk about the norms in a second. All right, define a suitable norm W. So then what you need to do is sort of you can assume, all right, and then you let D, so let that be a norm, and D be suitably large. Okay, then sort of assuming that this is less than 2D, you have to prove that this is less than D. All right. And that is the crux of the matter. All right, what is this norm? Well, there are different things that you can put. In this case, I'm going to do the one that's adapted to sort of null foliations and is also useful in the double null gauge. So first of all, and I'll motivate these things more in a second. All right, so there's sort of two parts to these norms. You should think is that there is a part which involves, so there are going to be certain number of derivatives you take. And there's going to be certain expressions that are valid no matter how many derivatives you take. Those are going to be sometimes called the high regularity norm, the norm that covers, well, this is a thing, also sometimes people interpose what they call the high regularity, the low regularity norm. Anyway, there's a certain part of the norm that will involve the maximal number of derivatives you can take. But the control that you get on these things, because it's for all derivatives, is weaker than some parts of the norm. Then there'll be some other part of the norm which you're only allowed to apply to less number of derivatives. All right, but that one will be strong. We'll have some like better control of the norm. All right, now let me immediately make that more concrete. So you pick some n, which needs to be suitably large. All right, in reality, suitably large might mean 4 or something. But again, when you're first like learning these things, it's easier maybe not. Don't worry about tracking how big that is. All right, just think that it's suitably large. Pick some n suitably large, some integer. All right, and what you do is, so you have this first part of the norm. So this is going to be a sum. So this norm is going to be a sum of a bunch of different stuff. So one thing that's in it is going to be all right, so let's call, so this norm will be a sum. This will be a sum of, I'll call it like this, high regularity plus low. All right, so the high regularity part will involve all right, this will involve what we'll see will eventually will justify our energy fluxes. So these are going to be certain L2 norms of the solution and derivatives along certain directions. So first one we're going to have a soup. We're going to look between from so from V, so for each V naught up to V minus 1, you're going to look at the integral of you're going to integrate on u equals -1 well, this always includes like there's a sphere everywhere, right? When I draw these diagrams, hopefully we're used to that by now. All right, so I'm going to integrate on the part of, well, not u equals, sorry. No, it's an integral over, maybe I should write it like this. Sorry. So integral over v, so for each v between v naught and v1, I'm going to integrate on the hypersurface v equals v tilde, but I'm going to intersect with the region that I'm going to control, right? So you can, the v equal, these are just diagonal lines, and depending where it is, you keep more of it or less of it, right? And so these are hypersurfaces. These are ingoing hypersurfaces. And then in this one, I'm going to put, well, yeah, and this will be, say, a sum over all these. They're going to be some, alpha will always stand for some multi-index, what I do right now. So I'm going to sum over, so up to, I'm going to take du of, oh, I'm putting f. So you should think that this f will be the solution to the wave equation eventually. All right. I'm going to put, so I'm going to take these du derivatives, and then this alpha is like how many things extra derivatives I've taken. So, which is like enough, which, like I said, in reality, it's like 4 or something, but all right. It's going to be du of f plus the gradient on the sphere of this, and then integrate it with respect to the natural volume form, right? So you'd integrate with respect to du and along the sphere. Or maybe I could write just for, right, that's going to be 1. And then I have the dual thing in the other direction. So plus, so now we do the soup, we just do the soup over u equals u tilde. Oh, and then again, I restrict in the region that I'm studying. And I'm going to put now dv. The angular derivatives come along for the ride everywhere. This is just stands for like a multi-index. So f of alpha, this is like d, t alpha 1, d, or you can think du alpha 1, dv alpha 2, d theta alpha 3, d5, whatever, just a bunch of derivatives up to which are up to that size. Yeah. All right, so that's the high regularity norm. Well, in fact, okay, this is just what's sufficient. Yeah, we'll use some other norms later. Yeah.
So we need this norm to choose all else. Is that what you mean?
Wait, sorry? You're saying things look a little self-referential because the size of epsilon will depend on the data. Yeah, the way I wrote it, that's correct. But yeah, so there's the epsilon that will make the theorem true, and then I'll need the 2 epsilon small enough. But this definition I can make for any epsilon.
Yeah.
Yeah, so it's just think I'm doing it for any epsilon. Yeah, that's a good. I mean, I'm being, well, you've picked out my lecturing style by now. Has some issues.
That's
I know. It's good to ask questions. Yeah, I'm going a bit informally because the thing is, if I do this like sort of properly in detail, first of all, we would get nowhere,
Yeah.
and you would fall asleep and be lost simultaneously. I mean, that might happen anyway. But all right, so that's like the high regularity norm. So the point is, these are what we refer to. These are energy fluxes. So these are integrals over null hypersurfaces, and they involve all of the derivatives tangential along the null hypersurface. So these are not like a full. These don't like just forget about this alpha. This is not the full like sort of, if you think about, if you've seen energy estimates for wave equations like along like constant T hypersurfaces in a normal PD class, that would involve like all the derivatives, like the full homogeneous Sobolev space. These ones miss certain derivatives. This is like we'll see, this is more flexible, but it's more complicated because, right, somehow depending on, you only control the tangential derivatives, the hypersurface. Yeah. These are just, yeah, energy fluxes. Okay, so then, and then we have, say, a low regularity norm. And well, again, like I said, when we prove this theorem later, we will I'm already running out of time here. We're going to we'll work with some variants of these norms, but roughly speaking, these I'm just giving you just the idea of the kind of norms that could be involved with such a thing. So low regularity. So these, like I said, this is a bunch of derivatives in L2 along different hypersurfaces. All right, then for the low regularity norm, you would pick some, well, the different things that you could do sometimes. So it involves some smaller number of derivatives. So for this kind of thing we're doing, you don't have to be precise. Sometimes you need to be very precise, but anyway, imagine it varies. So let's just say something less than 3n over 4. Example, 3/4 then. It doesn't really matter. It should be more than 1/2. And then, well, we'll just say something like the soup of, yeah, you can just do a pointwise soup, basically. That's sort of low regularity norm. So, and what's the, well, I guess because everything is, to make the scaling right, I should do it like this, right? What's a pointwise norm? All right, so this, so one, so version of way this kind of low versus the high thing might come up. So in like a normal space like initial value problem, there's certain, so you sort of prove some estimates like this via so-called energy estimates, and I'll review what how that works later. And then you sort of at some point in the argument you deduce kind of soup norm estimates from these integrated estimates by Sobolev inequalities. It's sort of exact, very one of the you know uh, very standard applications of Sobolev inequality. Many PDEs, like naturally from the PDE, you get integrated L2 estimates, and then the way you go from that to pointwise and Sobolev. All right, you can do a similar thing here. We'll do things. We'll see. There'll be a slight wrinkle in that the way we'll do things, but ultimately it's sort of the same. Okay, so these are the kind of norms that. So I claim that for this kind of norm, basically, if you prove, so you just have to prove that for this norm in G epsilon, you are less than D. And while you're doing that, you're allowed to assume that you're less than 2D. And this will be what we will, I mean, I'm sure I won't finish it on Wednesday, but that's basically what I want to show you how to do that. And along the way, like I said, we'll see sort of various important techniques. Okay, so I ran out of time to explain why this is enough. So I guess what I'm going to pick up on Wednesday is I'm going to explain why, or I'll hand wave a bit, as you can imagine, but I will vaguely explain why this is the heart of the matter. This is the hard work, is showing this, right? Which is kind of nice because yeah, it's sort of the opposite of some other areas of PDEs where, somehow it's like there's a formal argument which is like easy, but then, it's difficult because like you have a weird object and you don't know that you're like this easy, quote unquote, easy argument doesn't seem to make sense. And then the challenge is like, because you have some really weak solution. So in this kind of PD setting, it's like, it's the opposite. Like you can do whatever you want to the solution. It's a fine solution. You just have to show that this estimate holds. You can even like almost assume the estimate holds. So it's like the other extreme. But anyway, we'll see. All right, so it's 5, so I'll end there.